Thank you so much for having me. I'm really, really sorry I could not be there in person. I really wish I could, but the world had other plans, apparently. But yeah, I'm so happy to have this opportunity to be here anyways. Am I sharing the wrong screen? I am sharing the wrong screen. Great. Good start. Okay, that's the right screen. Yeah, really happy to be here. Super happy that I got to catch Sam's presentation. Sam, it's always a pleasure to see you speak. And my work sort of begins at a similar point as Sam's does, and we've been colleagues for a few years, and definitely exist within a very similar sort of discourse in a very similar world. But before I get there, I guess I'm gonna introduce myself a little bit more in detail. My name is Maria. I'm an assistant professor at the Daniels Faculty of Architecture, Landscape and Design, and a member of the Robotics Institute, both at the University of Toronto. I'm an architect, I'm a researcher, I tend to wear many hats. Oftentimes I'm not sure how to answer the question of what do you do? I do a lot of things. I guess first things first, I'm educated as an architect. I don't know if I identify as one. A very good friend of mine puts it very accurately, calling me not an architect, which I think at some point I should actually add to my CV. I generally practice robotics. So most of my daily routine time I spend designing and assembling machines. And all of that feeds into a practice that I now refer to as designing with machines, which is partially a response to robot-oriented design, where I try to design things together. So the object and the robot are being designed at the same time in an interdependent relationship. But before we go there, I wanted to briefly touch upon sort of, if not a history, but a bit of maybe a context of what construction automation and what is the relationship between a machine and a designer look like today, and what does that relationship used to look like? And of course, today we see a lot of construction automation progress, as I'm sure is being talked about at this conference. And a lot of the construction automation is happening within these two larger discourses. One is mobile and other types of machines for surveying. And the other one is automation of existing construction processes. So taking equipment that is already there, like this robot for position of heavy reinforcement arms, and then automating it such that it doesn't actually need a real-time human operator, or maybe only requires a teleoperator. And then, of course, there's another context that you're all familiar with, which is more of a research-driven, more exploratory context, where we're not necessarily looking into traditional construction methods, but we're looking into technology itself and trying to figure out what are new construction methods that it actually allows, and what are the design spaces that these types of technologies open up. And historically, this type of development and this type of investigation and research has really been spearheaded by researchers in architecture and design using robotic arms. That largely comes from a moment in time where they suddenly become available, and largely, of course, comes from the fact that they're extremely universal and reprogrammable and are capable of many different operations and many different tasks. However, despite the fact that we like to think about them as universal and reprogrammable, they actually come from a very specific place and a very specific set of tasks. They're generally designed for a construction, a manufacturing line where objects that are being produced are moving from one workstation to the other, and then machines continuously perform operations on them. And in appropriating or reappropriating this type of equipment from the manufacturing side and bringing it into architecture, we as designers sort of have to deal with a lot of constraints and limitations that these machines bring. One of the obvious constraints is, of course, reach, payload, the weight of the robot itself. If you were to imagine installing a machine like this on site, that comes with a lot of limitations. The structure needs to be able to support the momentum forces, et cetera, et cetera, et cetera. But also, of course, economical and cultural constraints, such as the very steep learning curve, which is partially designed to be that way and partially just happens to be that way. And of course, the cost of purchasing and running a machine like this. So somewhat in opposition to that status quo, and somewhat in addition maybe to that status quo, my practice lies around not necessarily interpreting and appropriating machines from the industry, but really trying to reinvent machines from scratch, almost sort of like reinventing the wheel, which may or may not be a productive undertaking, but I happen to enjoy this undertaking, so that's what I do. But within this designing of machines from scratch and designing machines that are not only task specific, but architecture specific and site specific, I'm trying to sort of add to this existing landscape of robotic and computational design research, and maybe try to rethink our relationship with machines. So at the core of this practice that I describe as designing with machines, even though I'm designing with them, in the end, I end up spending most of the time on the machine itself. And this journey started almost 10 years ago now with my very brief and very stressful obsession with spiders. The spider that you see on the screen right now is called Diane. She was my lab mate for a couple of months at the University of Stuttgart. I'm horribly arachnophobic, so that was not very fun, but also was really fascinating to spend the time and really observe the process of web building that these spiders deploy. So the reason why I chose Diane, or the Diane species, Tegenaria atrica, is this particular spider, builds these very intricate webs that are not just, the traditional kind of cartoonish orb web structure, but really three-dimensional complex structures that have different areas, like there's areas for feeding, there's areas for nesting, and there's areas for hunt. And maybe potentially more interestingly, these spiders really co-evolved with humans. So they actually prefer the rectilinear environments of our built spaces to natural environments for creating their webs. So they really like corners, they really like, spaces behind cupboards. They really, really like human environments as sort of their own tiny construction sites for their spider creations. So looking at the spider, one of the fascinating things beyond this coevolution is the relationship between the space, the body of, if we were to call a spider a machine in this context, the body of the machine, the scale of the structure that it builds, and its relationship to environment is this three-way dependency that becomes really interesting. So the body of the spider is way smaller than the structure that it builds, which is again, not very typical to our digital fabrication contexts. But also the web directly relies on the shape of the environment. So depending on the space in which the spider decides to build its nest, the geometry of the web will change. So sort of thinking about this interdependency between the three parameters, the site, the object, and the machine, I've started developing, potentially naively, but also in retrospect, in a very productive naivete sort of way, a first set of machines for fabricating in existing architectural environments. And the reason why existing architectural environments became really interesting to me is I really wanted to explore not necessarily this notion of building from scratch, which is pretty stereotypical to the field of architecture, but really the notion of revisiting, potentially repairing, and reprogramming spaces that are already there instead of building anew. So this particular machine is able to navigate its environment. The way it navigates its environment is it climbs along vertical or horizontal surfaces, but I guess the vertical surfaces is what matters. So it can climb walls. It can navigate. It knows where it is in space using an external camera system. It can carry a piece of material, and it can interact with another robot of the same type by meeting it at the corner between two walls and passing this material cartridge between them. It can then anchor the material to pre-installed anchors, and thus it's sort of, you can already guess, I assume, where this is going. By performing these three very simple routines, two machines working together in a space can start creating if not architectural, at the very least furniture scale objects in situ. And what is really powerful for me about this particular system is not only the use of mobile robots or the material system of web weaving, but how scalable the system becomes by using these really, really small scale machines. And when I say scalable, I mean not only scaling up, but also scaling down. And I think scaling down is not really talked about in architecture and construction as much, but I firmly believe that it's actually a very important parameter. So looking back at this project, kind kind of reflecting upon it once it was done and all the panic of the deadline wore off, I started to think about how the project was really initiated as this attempt to get out of the limitation of a robotic arm workspace, but then it got into a whole new set of limitations. Specifically, this system is limited to interior spaces where there are 90-degree angles. So if there were any sort of other geometries, the system wouldn't work anymore. Of course, it is limited by the tether, by the cord. The battery conversation is both my favorite and my least favorite conversation. We'll get back to that in the Q&A. So the next iteration, I was sort of reflecting on it and going back to this project and almost apologizing to the robot arm in my exclusion of robot arms from my work, and started to think how combining multiple different species, if you will, of robotic creatures could actually create more flexible and more modular workspaces. So here in this scenario, I have the same wall climbing machine, but instead of having two of them in the same space, I kind of add another small robot arm. That means that I can now extend my work envelope not only to just these two surfaces that you see in this video, but potentially more, even 3 or 4 or more, as long as they all sit within the reach of the robot arm. So even though the robotic system itself is not necessarily modular, the way these workspaces can be combined into a global multi-robot collaborative work envelope sort of starts to introduce a certain level of modularity that means that these systems are deployable in many different scenarios. So this project happens later. This one was conducted at the Milan Design Week. Here, the system is quite similar to the previous two, where we're relying mostly on the wall climber. But what is interesting here is, again, the multi-speciesness of the system now relies on a new type of machine that I call it many names. It's called a cable shuttle. It's called a thread walker, and it's also called Peter Parker. Depending on who I talk to, the names change. Peter Parker is frankly the one that really sticks the most because, you know, spiders. So anyway, in this collaboration, or I guess not collaboration, cooperation of these two devices, 3 devices of 2 different types, we can achieve this really extensive work envelope while keeping the size of the machine body the same. And not only does the work envelope grow, but also the opportunities to use these types of devices in spaces that are already occupied by humans are pretty unique compared to any other devices or any other larger scale machine. Specifically, if we think about a robot arm, it's hard to imagine an installation being built while people are walking underneath the installation itself. Just to briefly outline what I mean by the work envelope modularity, this project does a really good job at showing how combining two-dimensional workspaces of wall climbers and connecting them with the simple, very, very minimal cable shuttle really affords the full space that the interior space of this exhibition offers. The next project that I wanted to show you also lives within a very similar context of small machines working in cooperative teams and extending each other's work envelope. But here the context is a little bit different. This kind of continues the, no pun intended, I promise, thread of development of projects where well, the work envelopes are explored, but also I keep on kind of chasing the limitations and trying to get rid of them. So this project was developed to sort of live on a different substrate. So if the previous projects live on walls, this one lives on sheet materials. And as an experimental setup, the sheet materials were actually installed in the space, like were designed and installed in the space. But the theory is that a similar system could operate on any sort of architectural sheet material, be that a facade panel, be that maybe even the window, or any sort of system that one could imagine as a substrate for these fabrication processes. So here, the thing that changes is basically responding to the previous project and limitations in terms of time and tether. Again, battery question is the worst and the best question. So this system relies on a very different attachment strategy to its substrate because it does not require any sort of high power vacuum device in order to stick to the surface. these machines are actually battery powered, which means on one hand, yes, they can travel longer, but what is actually more important is the choreographies of their navigation along the surface become more complex and open up, again, new design spaces and new possibilities. And just like in the previous example, the combination of multiple work envelopes and workspaces really creates this overall robotic system workspace that sort of also serves as a design space on a designer site. I'm going to jump, no, wait, not yet. I'm not going to jump. Another project that I wanted to show you within this context is sort of a third iteration or a fourth or a fifth iteration of this idea of designing with robots and designing with robots such that they are site and task specific. Is this project that was conducted in a gallery. When I was invited to do this installation, I was really excited to sort of deploy a similar surface climbing system, but then I showed up on site and realized that the space that they were offering didn't really have any proper surfaces or any continuous surfaces for me to work with. So the system had to be reshuffled into a new sort of combination of, again, interdependent robotic entities. And in this case, the primary locomotion system for navigating the existing interior design substrate was a rail-based locomotion. So because the space already had a set of columns and beams, what we ended up doing is adding this extra layer of substrate that allowed for development of these sort of simplified locomotion systems that would drive on these rails, again, interact with each other in order to pass the filament from one machine to the other. Each of the vertical machines could navigate both the column and the beam on the ceiling, thanks to a special little arch or fillet piece of hardware. And similar to the previous project, over iterations and iterations of anchoring, passing, and anchoring procedures, the robots would eventually construct or wind this large-scale filament object that can, again, be occupiable, can be occupiable during the fabrication process, which to me is one of the most important parts of this research. And it sort of becomes both an installation and the performance. What was interesting during this particular part of the fabrication process is, well, I had to be there. There were certain issues with the sensors, so I had to really be there in order to operate everything live. You can see that I'm helping the robot and feeding it the material. But I was really hoping that people would occupy the space as the performance was ongoing, but somehow it was framed too much as a stage and people would not really enter the space. And another thing that I wanted to touch on before I move on to the last project is how in all of these, there's this modularity of workspaces, but also there's a modularity of the design process. So the way, when there's no machine to start off with, one has to really consider everything at the same time. And this particular diagram that sort of describes the way this project is designed is clearly very messy, and it's not really intentionally messy. It ends up being messy because the design process is messy. And I think for me, that is something that is really interesting with this type of approach, where one has to simultaneously consider the design of the fabricated object, but also the design of the shuttle robot or the handler robot. And within that, deciding which motor to use for the locomotion system creates this cascade of parameter changes throughout the whole design process. So for instance, if my motor is stronger, it can pick up more material, it can carry more material, so I can afford to use thicker material. But also if the motor is stronger, it's most likely larger. So I have to shift the anchor resolution a little bit further from each other. So it's sort of this loop of parameters where one has to jump from one to another. And when I started this research, I was frankly kind of pursuing more of a computational design approach. I was like, well, imagine this parametric system where you change the rail size and the motor changes. It's not really feasible because there's so much information trapped inside of these systems. And, that's not even talking about timeframes and budgets for, hardware purchasing. But through that investigation, what becomes interesting is that this sort of approach to designing and this way of thinking through mechanical and structural and design parameters can actually lead to pretty successful outcomes, despite it not being a computational or a parametric system. And maybe it only makes sense to have a parametric system where there really needs to be one. So I'm going to shift gears a little bit for the last couple of minutes of this presentation and talk about a somewhat different, but also very similar in ways, similar medium, different audience, I guess, project, which is currently ongoing. And we're currently on a third iteration of the robot. But basically, this is a project that I'm currently working on with Zaner, the fabricator, one of the biggest metal fabricators in the United States. I'm sure many of you are familiar, if not are working or have worked with them. So this particular project is a building that also many of you may or may not recognize. It's the Cadet Chapel at the United States Air Force Academy that was built in 1962 that is currently in need of significant renovation. And I'm not going to go into details of why and how, but the primary part of this project that I'm working on is figuring out how to install facade panels on a very, very complex substructure that was built in the 60s, and we don't really have a good understanding of what it looks like anymore. So of course, the first layer of investigation is figuring out what the structure looks like right now, which is done by laser scanning and really high resolution laser scanning. But what we've discovered is that laser scanning, while providing a pretty good understanding of what the structure is and where it is, it's not quite accurate enough for us to get into the second stage of this renovation project where we're installing these anchors for the facade panels. So that's the primary problem, figuring out not only where to install the anchors, but also how to localize them such that they actually provide enough accuracy for the facade system that is extremely, extremely high tolerance. So the solution that we've come up with is this, again, climbing robot, of course, because why else would I be on this project? But basically, it is a climbing robot that can navigate along the pipe substructure of the building. It knows where it is in space, and as it navigates, it kind of provides a secondary scan, but also as it navigates, it can mark places for the installation of the anchors. So the robot itself looks something like this. I wish I had it here with me so I could show you, but maybe next year. The machine, again, is designed to navigate this very, very, very particular type of pipe that the building is built out of. It is extremely site and task specific, but that is sort of why it is so powerful in the context of this particular project. So the machine carries this little Leica prism, which is basically a marker, which allows it to navigate itself in real time in space. And as it navigates, again, it gives us this digital model of the pipe. So the true steel pipe that is from our initial tests, that is always a little bit off of the digital model that we get from the laser scan. We have not yet deployed the robot on the actual construction site. We've been testing it on both pipe prototypes and parts of like the building mock-up prototypes. But so far, the testing seems to be very promising. We have some more exciting tests scheduled for the summer. And this particular model, I believe, is model 1. We're currently developing iteration 3, and I'm really excited to update you next year on how the project is going. But one thing that I wanted to say about this particular project, and one thing that is important in this context, to kind of demonstrate, is this project was fully done during COVID. I have not seen James in person up until a couple of weeks ago. The whole project happens via post and Zoom. Like the whole design process. I ship robots, I ship software, I get photos and videos back, and then we jump on a Zoom call and we troubleshoot. But it's amazing how the scale of the machine, frankly, really affords that. Like thinking about setting up something similar in a different manufacturing or a different fabrication scenario would be really, really hard to imagine. But this sort of works. We'll see where it goes. I'm going to show you one last video of our robot climbing on the actual building mock-up. And this is, I see I'm running out of time, so this is where I'm going to wrap up. And thank you again for your attention, and hope to see you all in person next year. Thank you so much.
Ooh, thank you. Can you hear me, Maria?
Yes.
Excellent. Thank you so much for getting up very early in the morning and our desperate times attempt to try and get you here failed, but we're going to have you back next year, which is great. I loved your presentation, and it kind of struck me that the kind of skill sets that you're showing here. You're an architect, you're a mechatronics expert to some degree, you're a programmer, you're an artist. How does one go about getting a skill set like that? What interested you in everything in the world, and knitting as well? Of course, knitting is a part of what you were showing us today.
Very good question, and I don't have a very good answer. I do have a weird echo though.
Oh, okay.
I'm gonna try and ignore it. Yeah, it's kind of my career and the way the practice is built. Sort of largely happened by accident. Like I got really obsessed with. Well, first I got really obsessed with design, and then I sort of discovered that the skills transferred into mechanical design, and then I got really obsessed with computation. And I don't know, it kind of built around many obsessions, and many times a hobby turned into a practice. And I think I'm finding myself yet again at a sort of intersection of decision making of like, but who do I want to be now? Am I more of a roboticist? Am I more of an architect? There is no clear answer, nor do I think there should be. But yeah, I don't know. I like wearing many hats. Yeah. None of them quite fit right, so I have to compensate with quantity.
What about the?
It's good hats.
Got you. What about the commercialization of what you're working on? What kind of avenues have you been exploring?
I have not. Partially intended. Like I get asked very frequently at talks of like, oh, but why don't you make a window cleaning robot? Why don't you start a startup? And I don't think that's me. If somebody else wants to start a startup, cool. You have my blessing. I really thrive in a space where I get to explore. My practice is really focusing on prototyping, not providing product. And I think that is something I've been learning about myself and about the way I like to work over the past few years. But that being said, the stuff that I showed you, the last bit that I showed you, the work that I'm doing with Zaner, I'm really excited to see how that changes the way these particular, like there's a narrow list of construction projects that we're thinking about in the context of this one. And in a way, we're automating labor, but also my sense is that the parts of labor we automate, like I feel pretty good about automating that part of labor. So I'm really curious to see where that goes, but I don't have any concrete plans on commercialization. I'm happy to stay in research.
that last robot seemed particularly unique. I don't think I've ever seen anything quite like that. So that's a unique design to you?
For the pipe climbers, yeah. Everything that I've showed today are robots that I've fully made from scratch.
Wow.
For better or worse.
Is there any other questions from Maria in the audience? Oh, okay, running over.
Thank you for the amazing presentation. It's very good projects. And I noticed in the first project that you have a camera to get the QR code and you can get the position of the robot on the screen. So I'm very curious in the last project, like the robot is on the PAP. So I'm very curious how you get the position of the robot on the PAP. So this is my first question.
Thank you. That is an excellent question. Localization is always part of any mobile robotic endeavor, almost annoyingly so. You know, you develop this really fun locomotion system, and it's like, oh, right, it needs to see itself. Ugh. But for this one, we're using a Leica total station, which is a piece of hardware that is often used in construction. It's really accurate. Like it just comes out of the box being accurate. We didn't have to really mess with the localization that much. So the robot is carrying a little marker. And let me see if I can share screen again to quickly show you. I don't know if you see my mouse, but I'm just going to assume it's you. So this orange thing, sort of backpack, we call it, is actually a machined piece of glass. And on the ground, we have the total station itself, which is basically looks somewhat like this. This is actually a good video. So this thing on the right is like a total station, which is basically a pan tilt head with a laser beam that focuses on the prism, gets a reflection back. So it gives you localization by measuring the pan tilt, orientation, and distance. And it just happens to be a very, very, very precise piece of equipment. And again, like they use it in construction, not with robots, but like with humans holding a marker usually for measurement. There's spot plugins to integrate like a total station. Like it's a pretty state-of-the-art piece of equipment.
Okay, thank you. So I have another question is how you plan the trajectory of the robot. So do you use the robot operating system or you use another way? Because I saw it cooperates really well and very amazing.
There is sort of an evolution of techniques and scenarios, but I keep on planning on integrating robot operating system, and I keep on staying in Grasshopper world. For this particular project, the reason why we're using Grasshopper and is because we're working with already existing Rhino files, so it sort of works for us. Because there's no it's not a very high speed application. Like as long as the robot eventually gets where it's going, fine. And also path planning along a pipe is not a very basically when we're path planning for this particular project, the two parameters that we have to take into consideration, or I guess three parameters. One is of course the tether. So this robot is not battery powered. It always has a cable, and there's no plan to make it battery powered because we don't really need it to be untethered. So you need to plan such that you don't entangle yourself. You also need to plan such that you're always in the view of the Leica total station. So making sure that the localization system always sees you. And there are some obstacles along the pipe in the actual, on an actual construction site that we also have to take into consideration. But even with those, it's a very simple geometry problem. And then once you have a path, staying on that path is also just a very simple feedback mechanism.
A final question is, what are you working with a particular laser scanner vendor or total station vendor? Or are you kind of taking it from cannibalizing existing machines?
Well, currently we're using Leica, the total station that Leica provides. I don't know why. That's Zainer's decision, but they do seem to have a really good accuracy and precision parameters.
So it stops and then does a scan. While if you use it's a SLAM type technology.
Not really, because it's not relying on onboard sensors. So the sensor sits on the ground. And the sensor looks at the robot.
I got it. Right. Okay. Well, thank you, Maria, so much for being with us, and thank you for getting up. And we're going to see you next year in person, so that'd be great. Maybe you can bring some robots. Excellent.
I would love to.
We will do it. Thank you very much. Everyone say thank you.
Thank you.